So chapter 3 is on polynomial functions, and 3.1 we are exploring polynomial functions. A polynomial function, by definition, is a function that has the form f of x equals an x to the power of n plus an minus 1 x to the power of n minus 1, and so on and so forth until you have ao as the last term, where an minus 1 are real numbers, and n is a positive integer and is also called the degree of the polynomial. So this number here would be the degree of the polynomial. It would be the largest exponent in value. So let's take an example. Actually, before I do that, let me just give you some examples. So for example, if you had a polynomial f of x equals x cubed plus 2x squared minus x minus 1, you can see that this polynomial has 4 terms, and the degree is 3 because that's the degree of the term that has the highest exponent value. And so we say here the degree is of this polynomial is 3. And you can see that the coefficient of the first term here is 1. It's understood to be 1. This is 2. This is negative 1. And the last term, it's actually x to the power of 0. And you can see how the exponents are decreasing by 1 in each subsequent term. You can also have, for example, if you have a function like this, let's say f of x equals x squared plus 1 over x. Here, the degree here of this term is 2, but the degree of this is negative 1, because when you bring this up, it becomes x to the power of negative 1, and negative 1 will not satisfy the fact that n should be a positive integer. Therefore, this is not a polynomial. Okay, so the degrees must always be positive integers. So this one is not a polynomial function. Another example of a function that's not a polynomial function would be, let's say, x plus square root of x, which is simply x plus x to the power of 1/2, where the degree is again not an integer. This is positive, but it's not an integer, so not a polynomial. Not a polynomial function, okay? Or if you have f of x equals, let's say, x squared plus x to the power of minus 2. Here again, the degree is negative, so it's not a polynomial function, right? There are other functions also that are not polynomial functions, like the square root function, the reciprocal function, the sinusoidal function, and the exponential function. They are all examples of functions that are not polynomial functions. Here we have some examples of functions, and the question is, which of the following functions are polynomials? State the degree for each polynomial. Here you can see f of x equals 3x squared plus 2x minus 4. It's a quadratic function. It is a polynomial function with a degree of 2. G of x here has a degree of 6. It is a polynomial function. This has a negative exponent, so it's not a polynomial function. Here also, the exponent here is x to the power of minus 1, so it's not a polynomial function. Here, the degree is 1. So it is a polynomial function. This is x to the power of 1/2. It's not. This one is x as the exponent. It's not a polynomial function. And this one here, the degree is 9. And yes, it is a polynomial function. So the simplest types of polynomial functions are what we've already seen: the linear function f of x equals x, and the quadratic function f of x equals x squared. The domain of this function is x is a real number. The range is x, y is also a real number. There are no asymptotes. There's none. Similarly, you know that the domain of a quadratic is x is a real number. and the range is y is also a real number, and there are no asymptotes. Okay, and you know, the simplest form of the parent function, the degree here is 1, the degree here is 2. And then we have the cubic function where the degree is 3. So this is an example of a cubic function. Again, you can see that x can take on any value from negative infinity to positive infinity. So x belongs to R is the domain, and same thing for the range. Y values can go from negative infinity to positive infinity. So y is a real number, and there are no asymptotes. You could also have a cubic function that looks like this. So both of these graphs are also examples of cubic functions, and they have the same domain and range as I've stated here. And on the right side, I have a quartic function, which has a degree of 4. So it kind of looks, in a very basic form, it looks very similar to the quadratic, but the base of the curve is a little more flattened out. And there are arrows here that point, because it goes on to infinity. You can have any value from negative infinity to positive infinity for the domain. So x is a real number. Same thing for the, for the range, you can see that there are no negative values, right, for this one here. So for this one, you would say there's a restriction. Y is a real number such that y is greater than or equal to 0, and there are no asymptotes. But for this, which is also examples of quartic functions, you can have, you know, y values that have restrictions on them based on the kind of graph you have. For example, for this green one, the y values will be, you know, the maximum they'll go up to is 6. So there's a restriction that y is a real number such that y is less than or equal to 6, right? Now we're going to go above 6. And for this one here, there's a restriction of y that says y is, the lowest it can go is, let's say, negative 6.5. So y is a real number such that y is greater than or equal to negative 6.5. So based on the function you have, you may have to indicate the restrictions. And these two are also examples of quartic functions which have a degree of 4. So you could have this shape, which is more like, looks like a parabola, but it's more flattened. Or you could have this shape like a kind of a weird W shape or W upside down. That also would be a quartic function. Next, you have a quintic function where the degree is 5, and it kind of looks like a degree 3 cubic function, but more flattened here. X can take on any value from negative infinity to positive infinity. Similarly, the y also. So x belongs to R, y belongs to R, and there are no asymptotes. Okay. This can also be a quintic function. It's another type of quintic function, which you can see that x is a real number, y is also a real number. They can go from negative infinity to positive infinity. Okay. So in summarizing, a domain of a polynomial function is a set of all real numbers. The range of a polynomial function may be all real numbers, but it may have a lower bound or an upper bound. So like this example here, it has a lower bound. It cannot go any lower than this. Or it could have an upper bound where it cannot go any higher than this. So there could be some examples or some cases where they could have restrictions. The graphs do not have horizontal or vertical asymptotes. The nth finite differences of a polynomial function of a degree n are constant. So if I have a linear function, then, you know, if I did the table of values, the first differences will be constant. For a quadratic function, the second differences will be constant. For a cubic function, the third differences are constant, and so on. And like I'm just made up a table here for a cubic function that goes from x values of negative 3 to positive 3, and those are the corresponding y values for f of x equals x cubed. I did the first differences, did the second differences, and then the third differences, and you can see now the third differences are all constant, and that makes sense because for a cubic function, the third differences would be constant. Okay, so those are the features and some of the properties of polynomial functions. So we want to just try out some practice questions now.